Hi everybody. Welcome to this online event on gravitational waves organized by the Netherlands Physical Society and the Virgo collaboration. My name is Ida Jekel and I'm the chair of the NNV. And before we begin, I must ask you to please make sure that your microphone keeps on being muted for the rest of this gathering. But let's start. Yes, most of you are members of the NNV, but for those who are not, let me start by explaining who we are. We are an organization by and for physicists in all fields, and we try to improve physics education in the Netherlands. We help teachers on all levels. We talk to politicians about our curriculum. And we make sure that the voice of physics is still strong in an ever more multidisciplinary world. And we convey the importance of physics in our society. So we strive to make it more diverse and inclusive. And in short, we are here for you and make sure that you can do physics in whatever shape, way, or form you deem fit. But for this, it is important to hear from you, to have you as a member. So if you are not yet, please help us to make your voices heard. So please consider becoming one if you're not yet one. And if you may, maybe you have physics colleagues and you could ask at least one of them if they're a member or not, and maybe help them considering becoming one. Because we can only make a fist if we have as much members as possible. And this is truly a time where science and scientists need to be heard. So help us help you and let us keep on spreading the word of physics. So I would like to thank the people at Virgo for making this possible, and especially Gideon Koekoek and the Virgo Outreach Group with the leadership of Dr. Livia Conti. And we are going to talk about gravitational waves. And I myself personally think they're really cool and really awesome. And I think that so many of you tend to agree, otherwise you wouldn't be here. And you probably know already a lot about them because you're all physicists, but gravitational waves speak to the imagination. You know, they were predicted in 1916 by Einstein, flowing naturally from his theory of general relativity. It took almost precisely a century to measure them for the first time. And on February the 11th, 2016, it was announced that the first wave was discovered. And it was such a momentous occasion because for the first time, mankind actually had a new sense. Up until that moment, almost everything known about the universe was gathered by looking at stuff. Electromagnetic radiation going from a source to our eyes, first directly via telescopes and later other electromagnetic waves like radio waves or X-rays, but they might be invisible to our eye, but it's basically more of the same. And this new sense immediately gave us a lot of information on, for instance, where half of our periodic table comes from, how black holes and neutron stars behave. And it was so truly momentous that the following year, the Nobel Prize in Physics was awarded to gravitational waves. Not often it is so obvious where the prize should go as it was in this instance. And I'm looking very much forward to our speakers and our panel discussion. So first we will get a lecture. And then you will have the possibility to ask questions to an esteemed panel of experts. So a short remark beforehand. Everything is being taped for prosperity, so please be aware of this fact. If you have questions, send them in via the chat. You could have sent them in beforehand via email, and we gathered all those questions already. But later for the Q&A, if you have questions during the presentation or later for our panel, please write them down in the chat and specifically directed at Gideon Koekoek. So look at the pull down menu and make sure that you write to Gideon. He will gather the questions and relay them. And if you want to ask it in person, please write it down at the same chat message that you want to ask it in person, and we'll try to make that happen. Otherwise, Gideon will ask it on your behalf. This way we can address as many questions as possible and make the best use of our time. So it is time now to introduce our first speaker, and boy, are we lucky to have them here. Professor Dr. Stefan Hild is an expert on measurement techniques of gravitational wave detectors and plays an important part in the work on the instruments of the Virgo experiment. Until 2019, he was professor at the University of Glasgow, and from that moment he chairs the gravitational wave physics group at Maastricht University. They are responsible for the building of the ET Pathfinder, a research and development facility for new detector techniques of gravitational waves. So if Stefan is ready, I would like to give him the digital floor. It will be your own floor in this strange situation, but at least I will transfer the honors to you to take over.
Okay, cool. Yeah, thanks very much for the very nice introduction.
Yes, gravitational waves, yes.
Very good. Okay, yeah. So thank you very much again for the nice introduction and the honor to be able to talk to you all today and share a little bit about the story of the last few years in our field and what I think is quite an exciting story of this new messenger that was already mentioned, these gravitational waves. Before I start, I should mention I'm talking here, you know, not for myself, but as you see here, there are big collaborations, the LIGO collaborations, Virgo collaborations, the Einstein telescope collaborations, and many, many other people who made all of this possible. So there are certain people in our field, colleagues, who actually dedicated the last 4 decades of their career to making this possible. Okay, so I'm standing here in front of you, virtually in front of you, for all of these people to tell a little bit our story. Okay, so where do we start? Let's get started a long time ago in a galaxy far, far away, and far, far away you can mean in spatial mode, or you can also think about time. And here we go back to, yeah, let's go back to when the dinosaur started, and then you just add another billion years, you go even further back. And then what happened was actually what you see in this video here, where you had actually 2 black holes. Do you see my cursor? Yes, okay. So you had 2 black holes performing in a very distant galaxy, a small dance, a circular dance, where they actually were radiating away some of their energy via gravitational waves. And these energy loss caused them to come closer and closer together. So we see the spins up, it goes a little bit faster. And I should mention, you see here the time up here. This is a very, very slow motion of about a process that took about a second. And then at the very end of this dance, and we see this here, these 2 black holes actually come so close together that they become one and merge. And that's happening here. That's this merger that we observed. And then afterwards, you see a little bit of in ring down from the whole thing. So that was 1.4 billion years ago, but then, as it was mentioned already, these gravitational waves were radiated away, traveled to space and time, didn't see much attenuation, and actually hit the Earth on the 14th of September 2015. And this is what it sounded like when, for the first time, we were able to listen to the, let's say, very first note of what some people coin the symphony of the universe, or Albert Einstein's symphony. So here you see hear the noise, I hope, or the signal. This is the original speed. It's a very low whoop, and if you play it a little bit faster, then you hear this characteristic chirp, this ice hockey curve where you go have this signal like whoop, and this is kind of the system spinning up until it actually merges. So quite amazing, and we were very lucky at that time, not only that we found gravitational waves, but that was kind of a discovery of many, many firsts. And I list here some of these firsts. So it was the first detection of gravitational wave. It was the first time we had a direct measurement of a black hole. We know that black holes were there, and we had some observations from X-ray binaries, but you couldn't directly see the black hole. There was the first measurement of a binary system of 2 black holes circulating around, and I think that's referring to why I said we were so lucky with this. It was the first observation of what I would call a new class of heavy stellar mass black holes. What do I mean by that? Here on this plot, you see on the y-axis the solar mass, kind of how heavy is a black hole. And all of these purple ones here are the ones we knew by 2015 from X-ray studies, okay? And they're all centered here between 5 and let's say 15 solar masses. the masses that we saw in this first merger of black holes that LIGO observed were massive compared to this. Even the components were kind of twice as heavy as the most heavy ones we had seen. And then you see these merged together into something in the 60, 70 solar mass region. And that was really amazing because immediately it changed, obviously on a certain amount, but it changed the view how we saw the universe, because we didn't expect to see these heavy stellar mass objects. By now, obviously, in retrospect, hindsight is always a good tool. Things look a little bit more reasonable. We know it's not surprising that we see them. But again, at that point, it was quite an interesting observation. And then the final one I find quite staggering is the amount of energy. We always say these events are very violent, but just to crunch down the numbers, you had this binary, and in a fling of a second, the energy emitted was about 3 times the mass of our own sun, okay, just going away. If you think about, how many billion years our sun will burn, and, thinking about also what fraction of mass is only converted in this process, having 3 solar masses completely converted in a second into energy is just amazing. And for a short period, this event outshone the observable universe by a factor of 50. So really kind of, mind-boggling numbers. And yeah, obviously we were all very happy. And here comes one of the important things why I said, this is, a big team of people. When we published this discovery, here you see the author list, and quite a few of the names you will see later or from the panelists for the question and answer session are actually on here. So there were 1,000 people who were authors of this discovery paper, and this is really a fully international effort. You see here it's 133 institutions from where this comes, like NICEF and so on. So a big international team effort, as you might have in many of these kind of big science discoveries. And yeah, the discovery obviously got quite some news attention. I think we were very happy that we got twice in a row awarded the Scientific Breakthrough of the Year by Science, and the Nobel Prize was already mentioned. So very, very happy, and really kind of, also for me, I mean, I do this for 20 years, quite a watershed moment. For 15 years, we were talking about, what we will do cool stuff with detecting gravitational waves, but we hadn't seen one. So this really marked a change in how, our scientific field developed. Okay, so that was kind of, the story, how it started. But let's think a little bit about this, how do we can actually measure gravitational waves? And Diederik mentioned it already. It took nearly 100 years to do this. Okay, so that's quite a big and long time from someone stating something to actually finding the evidence. Yes, this is right. So we need to, why it took it so long is quite an interesting story. And for that, I think we start with GR. I guess most people are aware of what GR is, but really kind of just to think about gravity was, until Einstein, Newtonian gravity was really expressed in terms of forces. But the question was really, how do two bodies on interstellar scales actually know of each other? How does it work together with no information is transmitted faster than the speed of light, but actually forces interacting? And the elegant solution we all know came with GR, where we know that space-time tells the matter how to move, and also matter tells space-time how to curve. And this is obviously the part where the gravitational wave comes in, because what we observe is the curved space-time from changing matter distributions. So they were predicted in 1916, and I always think of it as the kind of nice small anecdote that apparently Albert Einstein himself thought that these solutions to his equations, which actually gave the gravitational waves as a solution, were kind of a nice nice academic problem, but really were not of any kind of use or never be observable because they are so small. So by the time when people actually observed the first gravitational waves, you could say we proved Einstein right and that these waves exist, and we proved him wrong at the same time that nobody will ever observe them. So that was actually quite funny. So what are these gravitational waves? If you think about them, they are traveling through space and time, and as Diederik mentioned, they are not like electromagnetic waves. So if you would have a gravitational wave passing into your screen, and you would have on your screen some ring of test masses, then over time the shape of this ring would actually being stretched and squeezed, and you see this here in these blue bubbles. Or if you want to think of it in three-dimensional, you have this kind of wave passing through and changing kind of the diameter of a tube in there. How does it look like? If, for example, we take the discovery binary black hole signature, the waveform, and let it pass through the Earth, and this is a realistic waveform here, it's just that the scale is slightly exaggerated, then this is actually how the distances on Earth would have changed. Unfortunately, you know, or maybe fortunately, not on this scale, but at a much, much smaller scale. So these waves are actually super, super tiny. So how can we measure them? And here we turn to a so-called Michelson interferometer as a tool for measuring these. And what we do is more or less, we use the speed of light as a yardstick. So you do more or less a time of flight measurement. And we see this here in this video. You send a laser beam, you split it up into two perpendicular arms. And if you recall the picture I showed you how a gravitational wave acts, then it squeezes one arm and it stretches the other arm. And that gives you a differential signal. So the light will fly a little bit longer in one arm than the other arm before it returns. And then if you look into the interference pattern at the output to make a continuous measurement, then what we observe is constructive or destructive interference, or in reality, always something in between. And from the light level detected here on the output, this is really where we get the information of the length change in these two arms. And usually we operate it as a null instrument that you don't see light. And as soon as there's a bit of light, then we know something changed in the arm length. In reality, things are a little bit larger and a little bit more complicated. So this is a Virgo interferometer near Pisa, or one arm of it. So more or less the beam splitter you saw sits in this big building here, and we will have a look inside in a second. And then your light is split off into these two arms running 3 kilometers in this direction. And here in this box sits the mirror, and 3 kilometers in this direction. And then it's detected again here in the big box. And just for comparison, here's a LIGO interferometer. It's actually even longer, 4 kilometers long. That's the one in Hanford. So why do you have to make these interferometers so big? And this is shown in this cartoon here, because what we now do is really kind of show how big is the change of a gravitational wave, or the change that the gravitational wave introduces or induces in your change, in your length. So for example, if a gravitational wave passes by, I get a little bit taller and a little bit thicker one moment, and then I get a little bit shorter and a little bit slimmer the next moment. But the effect is tiny. It's only 10 to minus 22 of my own length. And if you now go to 4 kilometers, obviously the relative change will be a little bit larger, but still you see here it's tiny. Okay, so if a gravitational wave comes by, you see here we have our 4 kilometers. This is about here in the fourth or fifth digit, few hundred micron is your thickness of your hair. Here you get to the size of an atom. Then we go another 5 digits down, we get to the size of a proton. And then you see here, 1,000 or 10,000 of a proton on this length of the 4 kilometers. That is really the measurement precision that you need. And that's why it took actually 100 years to get to that point, okay? What we need to do such a measurement is a lot of high tech on all different types of physics, of engineering, and so on. So for example, all your laser beams, you can't just send through air because air is too turbulent. So you have to make sure the light is really not kind of disturbed by any kind of molecules or atoms flying through. So that's why you have to put it under vacuum. All of your mirrors and beam splitters sit in these huge towers here. They are kind of 9 meters tall to separate everything from acoustics, from seismic disturbances, and so on. Your mirrors are actually pure pieces of art, I would say. Very, very nice, super high precision optical elements, which are extremely flat. Nowadays, actually flat to atomic levels over nearly half a meter. And then all around it is obviously a bit more than just the beam splitter and these two end mirrors. There are hundreds and thousands of different optics and subsystems to make this whole system actually run. And that's why you need these hundreds and thousands of people to actually do such a measurement. Let me give you some examples, just a few, to understand where the challenges really lie. So one thing to think about is we want to measure now the change of about 10 to minus 22. So that means relative, if we think about something which is a few kilometers long, we want to measure something to the accuracy of, at one point, 10 to minus 19 meters, 0 point, and then 19 zeros and a 1 meter. The first problem you encounter with that, if you put your mirrors now somewhere, the ground all around us, because us moving, an earthquake, somewhere in Japan or whatnot, the ground moves always by about a micron, 10 to minus 6 meters, okay? So you need to go from this 10 to minus 6 to 10 to minus 19 meters, and you need to reduce the seismic signal by a factor of 1,000,000 times 1,000,000. Otherwise, you wouldn't see. Your signal is completely masked by all of the stuff around. So that's why you see here we have these kind of sophisticated seismic isolation systems, which more or less work very similar to what you have as a suspension in your car. When you go over a bumpy road, obviously the suspensions, makes you ride a little bit smoother. And that is more or less a seismic isolation system. It doesn't give you 13 orders of magnitude, admittedly, but it's the same principle. And we do many of these stages here. So you have pendulum stages and you have blade spring stages, very similar to what you have in the car for vertical isolation. And if you just combine many of these stages together, then you actually get to these factors of 1,000,000 times 1,000,000. But it's quite a lot of effort to go there. And that's why these things require so much engineering and so much work. Another example, as I said, are these mirrors. You need to bring them down to atomic level. So you need to polish them, really kind of that there's not any points sticking out. Otherwise, your laser beams will actually go slightly the wrong way, introduce additional noise and so on. So pure pieces of art, these mirrors there. Good. So we saw what we want to measure is really, really tiny. And the biggest problem in actually doing the first detection is to be sure that what we see is actually a gravitational wave and not any kind of other disturbance locally, to your detector. So there are many things. If we talk about this kind of, you need to move your mirror by a 10,000th of a proton diameter. There are bazillions effects which can do this. Okay, you might have the magnetic field of a train 5 kilometers away, which might be able to do this. You might have some lightning causing some acoustic noise. You might have power lines capping in. The biggest signal you see actually in a gravitational wave detector are usually the waves hitting the shoreline a few hundred kilometers away at the next coast. That's more or less dominating the RMS of the signals in this detector. So quite a lot of these disturbances in there. And the big question now is, and what many people worried about at the beginning, not worried within our field because we were feeling comfortable doing the right thing, but many people on the outside doubted, how can you actually ever measure this and how can you distinguish a gravitational wave signal coming from 1.4 billion light years away with a tractor passing by one of these kind of buildings of your interferometer. And there are two techniques which I think are very fundamental to this. One is these black holes we know have a signature. We know what we are looking for. General relativity and numerical relativity tells us, oh, a black hole should have this waveform here, so you know what you're looking for, okay? Very similar to my own signature, or you see here a signature of a rotating neutron star or a supernova. So we can use techniques called matched filtering, which actually allow us to really find tiny signals in our noisy data streams. And here you see what the reality really looks like. So these are the measurements of the very first gravitational wave. The other way how to look at this, more quantitative from the physics point of view, is actually to look at the significance of these events. And this is a fairly complicated plot. So I would like to take a few minutes just to talk you through what we see here. So what we do is we look for, maybe we go to the next one here. What we do is we use coincident within several gravitational wave detectors. Okay, so I showed you there's a Virgo detector in Pisa, there's a LIGO detector in Hanford, there's actually a LIGO detector also in Livingston. So you have several detectors in there. And each of these detectors, I give here kind of a time stream, and wherever I put one of these red blobs on there, there's some kind of a disturbance, some deviation from the operating point, and it could be a gravitational wave, very unlikely, or it could be a tractor, a train, or whatnot, much more likely. So how do I distinguish between these? I just look at these in coincidence. I know a gravitational wave travels at the speed of light and must hit the LIGO detector in America and the Virgo detector in Europe within 10 milliseconds. Okay, that's a travel time. If it doesn't do this, then it comes from somewhere else. So I really just do a coincidence analysis and say, okay, so here, for example, I have 3 events which are very closely timed in time. So I assume these might be an astrophysical event. So now how can I find out what is the significance of this event? And for that, we more or less break the timing here. And what we do is now we take the detector data streams and shift them by small amounts of time. So here, for example, I think I left the detector 1 the same. I shifted detector 2 a little bit to the left, detector 3 to the left. So I broke the coincidence. And if I now get a trigger which is kind of simultaneous, I know this can't be a gravitational wave, and I know that's pure coincidence. Okay, so this allows me to estimate my coincidence, or randomness rate for events just to occur because of the noise characteristics of my detectors. And if you do this now for all different kind of time shifts, then you get more or less this black line here, which shows you more or less on the x-axis here. That's an equivalent. Let's think about it like a signal to noise ratio. So the more to the right hand side here, the louder is my signal. And on the left, on the y-axis here, we have the number of events. And you see in general, my background falls off. Louder events are less often than very kind of faint signals here. And you see here, this is our background. And you see up here, that was a discovery event. Okay, so in terms of significance, it was far out, it was beyond the 5 sigma, and we were very, very confident that, and you put it in years, that this was really kind of had a coincidence rate that by random the noise would just give the signal would be 1 in 200,000 years. Good. So with that, we convinced ourselves, and I hope we convinced the rest of the world that we saw gravitational waves. And since then, we have moved on. There were certain other science runs we had, and by now we have actually published a little bit more than a dozen different signals, and we have this nice, what we call a catalog up here. The first gravitational wave transient catalog had 11 events in there. I know all of the astronomers beyond us laugh about catalogs with, a single-digit or double-digit number events. Usually you would have thousands or even more in there. But for us, having not seen them for 100 years, 10 events in a few years is still something we are very happy about. And, personally, I think I'm also very proud about that we have these. Good. So what came next? One more interesting part now was to actually look at multi-messenger astronomy. Okay, so we have seen black holes, but the next step was actually not only to see black holes, which are kind of not normal matter, but are pure curvature, pure space-time curvature. And we got lucky in 2017 to observe something different. And I'm not sure how well this works. That is now a very theatrical movie that NASA actually made out of this. So this is not just pure space-time, but this is matter and merging together. About that, because you have matter involved, some of the matter is expelled, and the effects from that are quite and very, very interesting. What happens when actually the matter interacts? It's not just point masses or curvature, but you have these meta interactions, lots of neutrons coming in one place to see that. And that was really kind of, where I think the next point was where people like me had, a shiver running down their spine. And that was this merger of 2 neutron stars. And what I show here is at that point, once we had localized and given people the position in the sky where to look for this object, more or less every astronomical instrument with some observing power, every piece of glass with observing power was pointing in that direction. So I was very kind of excited at that time to really see, oh yeah, Chandra is pointing in the direction that we just pointed to, Hubble is pointing in that direction. So it was really nice to see that all of the automated Twitter feeds, seeing them observing the binary neutron star system. And that was really kind of amazing, because now you not only combine your new messenger, the gravitational waves, and just have your new messenger, but you combine it with all different types of the electromagnetic spectrum. And I don't want to go into this busy plot here, but just to show you, so you had your gravitational wave signal coming in here, then you had about 2 seconds later, you had Fermi and GMB triggering for gamma rays. Then later we had X-rays, UV, optical, infrared, radio. So through the whole spectrum, we were able to observe this binary neutron star merger. And now coming back to my story of teamwork, it got even more amazing, okay? So we published this paper on multi-messenger observations. And this one had 4,000 authors from about 1,000 institutes, okay? So this is really kind of, some people estimate in the news, it was, oh, that's a third of the astronomy community of the world is actually part of this paper. Well, it was really amazing to see not only all of the gravitational wave instruments, but actually 70 telescopes from 7 continents plus the space being involved. I think that was really something amazing to see that actually coming together. Obviously, it's not easy to write a paper with 4,000 people, so I recall, stressy times, but I think it was worthwhile, and one of the things, I will tell my grandchildren about. So what did we learn from all of that? So one thing we learned was that GRB, some short gamma ray bursts that we observed with various satellites, are linked to neutron star in spiral. That was something that some people guessed on, but this was really kind of a very nice confirmation of that, that you see these two at the same time. Also very interesting is what happens if you now observe these two things, the gamma rays and the gravitational waves, and you see they arrive here at 1.7 seconds apart. It's more or less like you raise gravitational waves and gamma rays against each other and see which one is faster, or how far they are away. And this allows you to give amazing constraints on the speed of gravitational waves and actually the mass of the gravitons. So quite interesting effects there. The other part, which I think, just we put some, first steps in that direction. So we are not yet there, but what we could do with this observation was to look at the Hubble constant. So really kind of answering one of these fundamental questions: how old is the universe? How fast does it expand? And this was a completely new methodology, which is kind of independent of the traditional methods. So quite interesting. And I think that's something we will hear about a bit more over the next few years. We learned a lot about these very interesting objects, neutron stars, so really kind of very extreme matter, much more extreme than what we can actually test in laboratories. And actually, we had, after some conferences, people doing nuclear physics coming to us and really saying, look, you guys with that merger can actually do stuff, we were longing so long for to get done. So quite exciting, and, spilling out not only from gravitational waves, but also into other parts of physics. And then Diederik mentioned it already, what I think made the biggest splash in the news was always this kind of gold factory. Some people calculated how much gold was actually produced in this merger of these neutron stars. So what we could actually explain was, if you put many, many neutrons very, very close together, then this called the R nucleosynthesis will actually produce all of these elements you see here in this yellow area. So for example, where is gold here? Oh, I don't find it right now. Anyway, so you have gold and platinum and all these kind of things being actually produced. So the second half of the periodic table of elements, we can now actually explain by neutron star mergers. So again, I repeat myself, we were very, very lucky with the events we have seen so far, with the black holes, but also with the neutron stars. And yeah, you can argue that the gold for the Nobel Prize was actually also created in a neutron star. So that's quite a nice spin there. So the question now is, where do we go from here? What will happen? What will happen next? Obviously, we continue to observe, and you know, we just finished, or Corona actually shortened it a little bit, but we finished, you know, at 98% of the time we wanted to have an observing run with LIGO and Virgo, and we are currently analyzing the data, and there will be, you know, probably some interesting papers coming out over the next few months, which I'm not allowed to talk about right now, but watch the space, so there will be interesting things coming on right now. But where do we want to go in the long run? What comes next? And one of the big steps is that we want to go from the current facilities, which, you know, are marvelous, but were kind of really built as a first shot at gravitational waves, to go to, now that we are there and we know what we are looking for, to dedicated observatories. Okay, so, and this new observatory on the European side we call Einstein Telescope, on the US side it's called Cosmic Explorer, and this is really kind of a new class of gravitational wave detectors. And you see already, just by comparing the picture, that there are some remarkable differences. Yeah? The current detectors are all L-shaped interferometers, and they sit on the surface, while the Einstein Telescope is triangle, because it actually hosts 3 nested interferometers, and it goes underground. So quite different in the sense, so quite a big change here. And just to quickly mention one of the, or some of the main aspects in here, why do we actually have to go underground? And this underground has to do with the seismic motion. So if you think about it, you have mirrors actually being hanging in your vacuum chambers, and you're trying to isolate them from the ground via all of your suspensions to make them quiet. You would call this factor of 1,000,000 times 1,000,000. That's all fine. But at some point, you will also have the seismic will cause pressure waves in all of your ground and all of the areas around you, the volumes around you. And then you have kind of changes in your gravitational potential due to this pressure waves going through your surroundings. And this so-called Newtonian noise, you can't do anything about it. It's direct gravitational coupling, and no isolation is possible. And the only way to battle this is actually to go away from the surface, where you're dominated by the P waves, the Rayleigh waves on the surface, and go down where you're left with all of the body waves, but the body waves are much, much lower in terms of the seismic, and that's why you win quite a lot. I don't want to go into details, just give you some impressions of what the Einstein Telescope looks like. So if you would walk through a tunnel in hopefully 10 years from now or so, then you see it will look something like this. Everything will be a little bit larger and a bit bigger in order to get better sensitivity out there. And at least for my career, you know, engaging with the Einstein Telescope opened up some quite interesting avenues. So, for example, now I know a lot more about things underground, and I had a chance to visit places underground. You see here one of the panel members later on, Frank in the middle, you know, walking through some tunnels. And I know much more about actually concrete and how you build infrastructures underground. So quite interesting. Good. So where are we with the Einstein Telescope? We are currently trying to go kind of from the European astroparticle physics strategy, where the Einstein Telescope is one of the key elements, to go to the so-called S3, the strategy report on research as infrastructures in Europe. So this is kind of the roadmap for the big infrastructures to get on there and actually push the project forward. And the interesting part for the Einstein Telescope, or no, not the interesting, but one of the interesting parts, is that one of the site candidates is actually located, at least partly, in the Netherlands. So there are 2 kind of consortia proposing sites. One is INFN and supported by Italy in Sardinia. And then there is one consortium proposing to host the Einstein Telescope close to Maastricht, in the border region between the Netherlands, Belgium, and Germany. So now you might wonder, why actually Sardinia? And the amazing thing is, you know, if you think about Sardinia, many people think, oh, that, you know, it's close to the sea and so on. But it has an excellent geology, it turns out, and it has a very, very low seismic noise level. So you see this here, it more or less sits on a kind of very ancient, it's not sure whether it's really a tectonic plate, but it's something which is a body which is very quiet and, you know, not to be separated or mistaken for Sicily or other parts where you have kind of lots of seismic. So very nice, seismically, very quiet area. So that's one of the locations we are looking at. And then we are also looking into the Euregio and region in the three border region. So here some boreholes, we try to measure seismic underground, try to understand the geology a little bit better here. And the main reason to go there is actually shown here, because in this region in Limburg, what you have is you have different soil levels. You have a very soft layer at the top, and the soft layer absorbs lots and lots of the noise that actually humans make, cars make, and so on. And then if you go a little bit further down here, it's actually fairly quiet, also because you have an impedance barrier from the kind of very soft soil at the top to the very hard rock at the bottom. So all of the seismic, which is not dampened out, is then to a large fraction actually reflected. And you see this here for in this plot, where you have the seismic levels. Don't worry about the units here, it's really kind of just a relative measurement of the surface in blue. This is what the noise is on the surface, and you see during day times it's more because people drive around and move around. And more or less, you get a factor of hundreds to thousands reduction if you go 250 meters deep. So that's really the reason why we want to go down there. And if you want to see more of the details, it's actually published up here. What do we do in order to prepare for ET? One of the things that I'm very much involved with is building kind of a technology test facility. Kind of, you know, you take ET, you cut out of the 10-kilometer arms, you cut 9 kilometers, 990 meters off, and then you're left over with just 10 arms. And then you build an ET in short, and that's what we are trying to do right now in Maastricht. And I just give you a short video and we'll talk a little bit about there are 4 key aspects to this where we think about the technology that we need to develop. The Einstein telescope, in order to be so much more sensitive, needs to cool down the mirrors to reduce the Brownian motion in there. And in order to get to this new cryogenic temperature, you need to make sure that you have very, very quiet cooling systems. If you think about it, you have your fridge, which is the cooling system we all have in our households, makes quite a lot of noise. And this noise you somehow need to decouple from your mirror, while obviously the cooling you need to get to your mirror. In order to have cooled mirrors, we can't use silica anymore, no glass anymore. But what we have to do is we use a new material, which is silicon. And you see there's a whole lot of different physics if you go from silica to silicon. If you go to silicon, we have to use a slightly different wavelengths. So that's also something we have to engage with. And then there's quite a lot of topics that I didn't touch on right now, which are, I switched this off, I'm not sure how well you could understand me. So there's quite a lot of technologies related to how the measurement process, how can we actually make the detectors more sensitive from the quantum mechanics point of view of the measurement, because right now with advanced detectors we see, and that's a completely different story for a completely different day, I would say, are limited by an equivalent of the Heisenberg uncertainty in the measurement. And that's another topic, and one of the panel experts is an expert in these kind of quantum noise reduction schemes. Good, so that's ET Pathfinder. There's lots of universities involved. Again, it's a big collaboration effort there. Okay, so I hope I gave you a little bit of an overview of our story. Let me just summarize a little bit to think about where we are and what we want to go. So what I showed you, kind of some of these science, talking about cosmology, talking about the R processes, neutron stars, GRBs, all these kind of different, you know, mapping our universe with black holes. All of this we have from the current observation of gravitational waves. And if you stick these all together, we are still talking about seconds, not minutes, not hours, not years. It's a few seconds of data that we have from which we get all of these observations. So now comes the big jump. Now, if we think about the Einstein telescope or cosmic explorer, third generation detectors, then we will go from seeing something in the sky for a second once a week, we go to about 100,000 to 1 million signals a year. Okay, we are in a completely different scenario here. And you can do the most amazing things with that. So for example, every stellar mass black hole merger you will see with ET. Okay, it's not anymore, can we look further out? No, with that, you know, for the mergers, we are already at the edge. It doesn't make sense to go even further and make more sensitive. For other processes, of course, you know, it will be nice to go even more sensitive. But for the black holes and stellar mass, you have them all. And that allows you really kind of, you know, like thinking about the universe, reading, you know, flicking through the pages of a history book of the universe and really map out, you know, the populations of black holes. What does this tell you for galaxy formation and so on? So quite amazing. And then there are many other aspects like, you know, shedding light on dark matter, dark energy. We didn't talk at all about supernova and other aspects, or fancy things like, you know, what is actually the interior of a black hole. Is it really kind of just curved space-time, or are there actually structures like firewalls and other funny things in there which quantum gravity or string theory might suggest to us? So quite exciting times ahead, and lots and lots of nice, interesting physics in front of us. And this will really happen with advanced LIGO Plus upgrades, advanced Virgo Plus upgrades, which are underway. I didn't mention at all CAGRA, which is a detector which is currently on the way. And I didn't mention LISA at all. So there's a parallel effort to in 2030s to have a satellite mission up there to fly and measure gravitational waves at a much lower frequency to look at supermassive black holes. And then we have the Einstein telescope, cosmic explorer, and then even going down to very low frequencies, pulsar timing array, and many other projects. Okay, and I think here I stop with the overview, and thank you very much for your attention.
Thank you so much, Stefan, for this amazing presentation and this glimpse into the Einstein telescope and the future. And I'm sure people, yeah, normally you would get a big round of applause, but I'm sure that the people are standing on their bench right now and applauding there. So if you were measuring right now at Virgo, you would definitely pick up the applause from what you just did. So we collected all of the questions, or at least Gideon collected all of the questions for the question and answer part and the panel and on the presentation you just heard from Stefan. And it is a panel of experts on the field, and also the Gideon who's chairing the question and answer part is also an expert. He hates it if I call him like that because he thinks he's just passing on the question, but at least he's a knowledgeable passer because he's assistant professor at physics at Maastricht University and works at the research group of gravitational waves and fundamental physics. And he divides his time between research and the curriculum in fundamental physics. So without further ado, Gideon, please take it away.
Thank you, Diederik, for the introduction, and also, of course, to Professor Hield for the nice lecture and the overview, and of course for everybody here who is here on their Friday afternoon to listen to this exciting developments. Yes, indeed, we're going to follow up with the Q&A session. As Diederik already mentioned and Noortje already mentioned, we invited the audience to ask us questions. They could do so before the lecture started in the last few days. They could also do it during the lecture. So this is why I was offline for a bit, so I could collect the questions, and I will delegate them to the panel. Now, it so happens that of the 4 panel members that we have, or including Stefan Hield, 5 panel members, one of them has a somewhat prior obligation, so she has to leave in a bit. So I'm going to sort of reverse the role for a moment, and I'm going to relay the questions that are best answered by her directly to her, and after that I'm going to introduce her. Yes, so I won't waste any time to introduce who she is. So Tanja Hinder is who I'm talking about, who is an expert in gravitational wave modeling. She just switched on her camera. So Tanja, without further ado, and other panel members, don't worry, I will introduce all of you properly, but let's make sure that Tanja can make her other arrangements and have the audience questions answered. So without further ado, Tanja, I will directly jump in. A question that was asked online before the meeting started. If you see me look at the other side, it's because my my question screen is at the other side. physicists have identified many types of particles and matter and such. If you have a couple of neutron stars colliding with each other, some of these particles are turned into gravitational wave energy, right? Gravitational waves carry away energy. And the questioner asks which of those particles are turned into gravitational wave energy and which the ones get spared.
Oh, well, that's a very difficult question because so actually one of the features in general relativity, as Stefan already explained a little bit in the beginning of the talk, is, you know, we have to deal with curved space-time, and it's very difficult, for example, to localize energies. So I think it would be very difficult to label all the particles and then assign which ones get turned into energy somehow. Yeah, so I mean, we don't have a concrete answer to that at the moment.
Does this have to do with the difficulty in combining general relativity and quantum mechanics on that scale?
Yes, that is also one of the problems, yes.
I see, because the question indeed was sort of already presuming that this is going to be the answer. He asks whether there exists a way of calculating Feynman diagrams in a curved space-time when neutron stars collide.
Well, there are actually some techniques that sort of use all the tools that have been developed for particle physics in terms of Feynman diagrams to compute motions of black holes in some approximation. So using all the machinery that has been developed and applying that to computing black holes motion.
I see. And a follow-up question. I'm going to at a brisk pace because of your obligation in a moment, Tanya, so forgive me for that for a moment. A question that another questioner asks is, but if you have stars or neutron stars or black holes falling into each other, why is it that something gets sent out at all? Isn't it true that black holes would suck in everything, including their own gravitational waves?
Yeah, so they don't suck in everything, only if things that are close enough to them. That's kind of, yeah, there's a certain critical distance from the black hole in some sense where if you go closer to that distance, things fall in, even gravitational waves, but otherwise things can escape.
Yes, I'm sure people are aware this is the event horizon that you talk about, and gravitational waves will be already being sent out before they cross each other's event horizon or so.
Yeah, so I meant more even the light ring, where even light, as you might know from the maybe event horizon telescope pictures, you see the dark region in the center. Is not exactly the event horizon, but it's related. It's some outer distance, but related.
3M versus 2M. One final question, Tanya. What are the main unknowns for your work to calculate accurate waveforms for neutron star collisions?
Yeah, so as Stefan mentioned, we don't know the equation of state of neutron stars. We don't know what kind of matter is in the interior, if there is some transition to new phases of matter that we don't encounter on Earth at all. Also, yeah, we need to have better predictions for all the possible effects that material objects imprint on gravitational waves compared to black holes. Yeah, so there's still a lot of work to do, but we've also understood a lot already.
Yes. Do you expect that input to come from particle physics or from gravitational wave physics itself?
Probably a lot will come from gravitational wave physics, because that's really the new experimental probe of matter in new regimes. But also there will be some theoretical progress that will help.
Okay, thank you very much, Tanya. As I promised, I will actually now start introducing the panel proper. So Tanya, thank you very much for your contribution and for the answers to the questions. Having said so, it is indeed my honor now to introduce the panel. We have experts from the Virgo collaboration collected together who will give a nice overview of different subfields in the collaboration. So in just alphabetical order, let me go through them. One of the experts in the panel that we have right now is Dr. Sarah Cordial. She just switched on her camera. She's waving right now. Sarah is a researcher, senior researcher at NICEF in the gravitational wave group and of Utrecht University. She's an expert in the data analysis and the detection of gravitational waves from the noise. And she's starting her own group. And I think, Sarah, it was 3 years ago in 2017 that you came to join the ranks of NICEF and the Netherlands gravitational wave efforts, yes?
Yeah, that's right. Right before we had our big binary neutron started.
Yes. So as if somebody had a good idea, well, let's get this lady here because we're going to have some nice work cut out for experts. So thank you, Sarah, for being part of the panel. The next in our panel in alphabetical order is Dr. Stefan Danilishin. He's waving right now. Hi, Stefan. Stefan Danilishin is an associate professor of physics at Maastricht University. When we speak, he once told me that he is sort of at the fringe of theoretical physics and experimental physics. He is a theoretical physicist working on the quantum mechanical aspects of light, but he uses that knowledge to improve the gravitational wave detector techniques. So he can tell us a lot about how to circumvent Heisenberg's uncertainty principle that Stefan Hield already spoke about in his main lecture. So thank you, Stefan Danilishin, for being with us. We have some questions for you in a moment, of course. Moving on with introducing our panel, well, there is Tanya. In reverse order, let me introduce her as well. As you could already tell, she is an expert in gravitational wave modeling. She combines her knowledge of general relativity in curved space-times of that of nuclear physics to give accurate predictions, calculate accurate predictions of what the gravitational waveforms would look like on the different scenarios for colliding astrophysical objects. She has been at Nijmegen University before. She's now a researcher at UvA, and she has just left, I think, but it was good to have her for a bit. Moving on is, last but certainly not least, is Professor Dr. Frank Linde. Frank is, he's waving right now. Hi, Frank. Frank has a very distinguished career in physics because he actually started out as a particle physicist, being the head of the Dutch branch of Atlas for many years. Then he moved on to become the director of NICEF in the mid-2000s. And as of a few years ago, he leads the Dutch efforts in gravitational wave physics. So we're very happy to have him. He also asked me to say that he's also very good at kite surfing, just to balance out a little bit that he's not just a physicist. So thank you, Frank, for being here. And of course, we also still have Stefan Hield, who you just heard the lecture of. So we have a very nice panel. And it's also very nice to see that in Virgo, we don't have just people from the Netherlands, even though they're all stationed in the Netherlands, because all the panel members come from different countries. And it's very nice to see this global effort that Stefan Hield already spoke about, that so many scientists come together to make such a beautiful series of results. And there's many more to come. So, having introduced the panel, let's move on to the questions. Again, if you see me look at the other side, it's because the questions are mostly there. Starting immediately in no particular order. Question that we have here, maybe this is a question for Sarah, but of course everybody is free to weigh in at any time of the panel. A question that was asked by Hans Dachar is, suppose that there are more black holes, heavy black holes than expected. Does that change the predictions that you can make about the amount of observable mass and dark matter in the universe?
Yeah, so I guess one of the big questions is some component of dark matter just dark objects like black holes and things. So if we start to see that there's more black holes than we were predicting from astrophysics, we can start to ask, okay, where are these black holes coming from? There's some indication that we might see a primordial black hole population. So these would be black holes that form from energy perturbations in the very early universe. So they're very old black holes. And those would have a different kind of population characteristics than the ones predicted by stellar mass black holes. There's also prediction that some black holes could have clouds of dark matter around them. Not all, but some. And if we start detecting lots of black holes, we might start seeing little features on the signals coming from these black holes that could tell us about these clouds of dark matter around them. So yeah, I think there's detecting more black holes is definitely good for starting to probe dark matter in general.
Would you be able to tell the difference between a black hole that has no dark matter around it and a black hole that does have dark matter around it? Do they have different signals, to say?
Yeah, there would be, well, it depends on how much the dark matter is affecting the signal that we receive, but there's some indication that it will affect the phase of the evolving waveform that we receive here on Earth. So if the phase is shifted by an amount that is not exactly predicted by pure GR, then we know we have to add a little correction that's due to something. And if it matches the predictions due to this cloud of dark matter that causes the black hole to spin differently. Yeah, so it's mapping all of these little effects of the system to the signal that we see here on Earth.
But the predictions for the influence of dark matter on the gravitational wave signals, those are well understood enough that you can actually detect them as such or identify them as such.
I don't know if I'd say well understood enough, but people are definitely working on it. In fact, at the University of Amsterdam, there's a group that's looking at modeling signals coming from these systems with, they call it a dark matter dress. It's a dress around the black hole and how that affects the signal. So yeah, there's still a lot of work to be done there to understand how dark matter affects the gravitational wave signal that we see.
So final question along that line, could it be that maybe there was already a detection of a dressed black hole, but just not identified as such yet?
That's definitely possible. Another thing that we're looking into is, so astrophysics predicts that black holes, stellar mass black holes should exist from a mass range of about 5 solar masses up to about 50 solar masses or so. There's some boundary, you can shift the boundaries a little bit. But beyond that, there's really no theory from astrophysics that explains how black holes could form at lower masses or at higher masses. But we've started to see evidence for black holes in both of these regions at the very low mass end and at the high mass end. And so we're starting to ask, okay, maybe there's some other mechanism outside of normal stellar evolution that is forming these black holes. Could they be primordial black holes that formed from the density perturbations in the very, very early universe? Could they be other types of exotic objects that are not black holes, like dark matter stars, for instance? All kinds of interesting things.
That is very interesting. So just to make the difference very clear, you were talking about the normal, quote unquote, normal black holes that come about because very massive stars implode on themselves. But you also say that in the very early universe, density perturbations, just having a little bit more energy over here than you had over there, could also have formed black holes by themselves.
Yeah, they would collapse to form a black hole.
Yes, and those are the primordial black holes that you were referring to.
Right, and they could form across a whole range of masses beyond what stellar astrophysics predicts.
Okay, and those have not been detected yet, no?
Well, we've got some evidence for some. We've had a paper come out recently, so I'm not saying anything I shouldn't.
No, I understand. I was just trying to smuggle a scoop out of there, but we'll leave it for the people to read in the journals later. Yes. Let's move to some instrumentation. And so I have a question for Stefan Danilishin. A question that was asked in the chat box during the lecture was, in what way is Heisenberg a hindrance if you want to make better and better gravitational wave detectors?
Okay, yeah, that's an interesting question. So basically, Heisenberg uncertainty principle enters the gravitational wave detection field through by means of everything being a quantum mechanical entity, including the laser light that is being used to detect the motion of the mirrors. So there are many aspects actually, but what we directly detecting is the light that goes out of the interferometer and hits the photodetectors. And light has observables like phase and amplitude, and these observables are actually conjugate. So, and they obey the Heisenberg uncertainty principle. So basically, you want to measure the phase of the light reflected of the two arms of the interferometer as precisely as you can, which basically means that you reduce the uncertainty of the phase. But as a result, you increase the uncertainty of the amplitude. And the amplitude actually what defines how the light interacts with the mirrors. And if you have increased uncertainty of the amplitude, it means that the uncertainty of the energy with which photons interact with the mirrors, basically reflect off the mirrors and transfer certain momentum to the mirrors. So that creates a disturbance on its own on the motion of the mirrors and mimics the gravitational wave. So this is known as the back action, quantum back action effect. So, and as a result, trying to increase the sensitivity of your measurement, you at the same time disturb the measured object. Mm-hmm. And there is, of course, a kind of a trade-off, a seesaw situation, and you have to, to be quite clever to get as much information from the interferometer as you can, not disturbing the quantum nature of the quantum nature of this device.
Yes. And now all of us know the quantum or the Heisenberg uncertainty relation on this as this completely unbreakable barrier in quantum physics. There's just only so much information one can get from a system. Do we have clever tricks of circumventing that at all?
Of course. Well, you do not circumvent the Heisenberg uncertainty relation because it's actually quite a flexible thing. So there is no, how to say, no barrier, impenetrable barrier to reducing the uncertainty of one of the quantities. Mm-hmm. So the clever strategy deals with how to make the other conjugate observable not to affect your measurement. Mm-hmm. So, and that, of course, can be done. One of the things which I'm working on is, for instance, another slightly modified scheme of the interferometer that is called speed meter, where you measure the not the distance change between the mirrors, but rather the change of the velocities of the mirrors. And it can be shown that if you do that, then the back action I was talking about in the first answer gets significantly reduced. Mm-hmm. Yeah, there are many other tricks that can be used. So the problem is that everything which is related to the quantum behavior of such objects as 40-kilogram mirrors, so it's very difficult to observe in practice. And it took 30 years for LIGO, for instance, and Virgo to reach the level of sensitivity where quantum effects become visible.
Does it mean that we can say that gravitational wave detectors are also very good as quantum mechanical detectors?
In principle, yes. It was an interesting project I worked on 10 years ago and still do some work on it, so, which was basically called macroscopic quantum mechanics. The goal of this project was to find some ways to use the data from the gravitational wave detectors to prove that macroscopic objects, like for instance mirrors of the LIGO or Virgo interferometer, behave quantum mechanically the same way as elementary particles, for instance, do.
See, so it turns out that you can actually use gravitational wave detectors then to even probe the nature of quantum mechanics, to test that as well.
Not as yet, but we're very close to that.
Okay. So will there be Einstein telescope close, or can we already expect this to happen within Virgo or LIGO?
Actually, Einstein telescope will be closed, and to that, although it will be quite busy with collecting the astrophysical data. So, and usually the experiments on observing macroscopic quantum behavior requires shifting the interferometer into a slightly different regime. But when Einstein telescope or Cosmic Explorer are online, so the current gravitational wave detectors will be, so to say, it's a hope. Of course, I don't know. So more, how to say, more positive about doing some other experiments.
I see, but sir, but in 15 years, Einstein telescope, we will know better, yes?
Yes.
I see, okay, exciting times ahead. Frank, there's a question that I think could be best answered by you. The question was, how many gravitational wave telescopes does mankind actually need? At what point does adding more gravitational wave telescopes stop being beneficial?
For sure, you need at least 3, because you would like to pinpoint the sources on the sky. So that's the minimum, I would say. Mm-hmm. And yeah, on top of that, it's also very safe in view of noise. So the statistics that you are very sure it's a gravitational waves to have more than at least a few. Mm-hmm. Yeah, if you have infinite money, then I certainly would build a few more. You should also realize, if you look now at the electromagnetic instrumentation, which has given us a lot of insight, how many telescopes are there? I mean, you have radio, Röntgen, visible light on the Earth, in the sky. So I could also dare to say, if all mankind built 3 of these facilities in the future, so let's say Einstein Telescope, Cosmic Explorer, and let's say 1 in Asia, is that really a lot? I think that's the bare minimum. It's a completely new window and will give us a lot of excitement, notably to youngsters, and yes, thereby attracting lots of, let's say, future scientific wizards to our society. Because I cannot resist saying physicists. In fact, that's pretty silly, of course, because we are all physicists. But most of them were like me. They were attracted either to study the smallest of the smallest or the biggest of the biggest. And luckily for our society, a lot of them went elsewhere and did something, between quotes, let's say, useful. And some of us had the privilege to continue forever in pursuing their dreams. But you attract them by the biggest of the biggest and the smallest of the smallest. So I think our world, not only the Netherlands, our world deserves at least a few of these future generation gravitational wave detectors.
Yes.
By the way, I'm not a kitesurf expert. I told you I am a beginning kitesurfer.
Okay, let me correct that. Frank, for everybody here and for the recording for prosperity, Frank is a beginning kite surfer. But I'm sure in 15 years from now, when we will know more about quantum mechanics in gravitational wave detectors, this will also be the time when Frank has become an expert in kite surfing. So we'll get back to you in 15 years from now. But following up in all seriousness, Frank, you made a very charismatic plea that everybody gets super excited in the physics community when you look at the very small or the very big, and you are one of the people who have actually done both in your career. So everybody, I think, will agree that it's very useful and very exciting to have many gravitational wave detectors, but your somewhat more objective answer is you're actually going to need 3 in order to do sky localization. So that's
correct, and to some extent Einstein telescope has already multiple interferometers in itself, so that helps already.
Yes.
And for some of the sources, I think it was also made clear by Stefan and I think also Sarah, if the sensitivity goes up, you see sources quite long, okay? We might even see some sources for a whole day. Mm-hmm. And then we can use the nice turning of the Earth already to help the sky localization. So in the end, yeah, I don't want only one, okay? But if we only have one, we also will make the best out of it. That also helps already. But I think the Americans and Europe for sure should build a facility, a next generation facility, I mean, after the LIGO and Virgo and Kaga live.
So does it mean if for some reason the US decides, or will Einstein telescope by itself be enough?
I can also tell you, I myself am mostly interested in the details of black holes. And black holes, you are not going to study with electromagnetic telescopes. So my own interest is really in the details of the gravitational waves itself, the general relativity and black holes. So for that, I'm not so sure I need the sky localization, but I think the wealth of physics you can get out of, for instance, the binary neutron star mergers, binary and a neutron star black hole mergers, for that you really deserve to have excellent sky localization.
Yes. Yes, that's indeed a very good point. Now, of course, everybody here would like to have as many gravitational wave detectors as we can. All of us have one in our backyard. Maybe one for Stefan Hield. You mentioned, this was a question from the audience, you mentioned that you need a big gravitational wave detector, just in dimensions big, many meters, to measure smaller and smaller wavelength. Frequencies. Does that mean that at some point there's just a natural limit to how small a frequency will we be able to measure? I mean, at some point the amount of space runs out, yes, to build gravitational wave detectors in.
Yeah, if you think about the current technologies, I think that's true, and there's something that people call the seismic wall, and that sits roughly around 1 Hertz. And the key thing here is really kind of that in order to get this factor of a million, you can't use active systems. You can't just measure and correct for the disturbance. That doesn't work for factors of 10 to the 12. But we need to have these passive isolation systems, like these springs or like pendulums. And if you now go back to your first year physics and the resonance frequency of a pendulum and how it relates to the length, then you realize that it's very, very hard to go much below 1 Hertz with the resonance frequency of your system. You might, if you hang a Foucault pendulum for 50 meters or so, you might get to 100 millihertz or something like this, but it's very hard to get even below. So in that sense, I would think 1 Hertz is probably a limit if you want to do something here on Earth, but you don't need to go even further down, because at that point, space becomes much more efficient. So there is a LISA instrument, which I mentioned, which will fly in 2034 or so. It's one of the kind of really kind of on the map ESA missions. So it will fly, we know that. It might change a year or something like this. And something that some people are quite excited by is because you see them in a much lower frequency in LISA, there will be certain black holes which you see slowly turning in the very early state of the merger in LISA. And then, a few years later, or if you're getting closer and then Einstein telescope is where you can move it down, let's say a few days or a few weeks later, they actually spiral into the band of the Einstein telescope. And then you can see the same source in different frequency bands with different observatories on the ground and in space. And I think that will be quite amazing and exciting.
This relates a little bit to what Frank was saying, that it's good to have many gravitational wave detectors. Just as in the optics, you have multiple satellites and multiple telescopes of different frequencies. Yes, it's complementary rather than superfluous at some point. Yeah. This actually relates to a question that was asked by 2 people independently. That has to do with if you have a very sensitive gravitational wave detector, then you will have many overlapping signals. In fact, Stefan Hield, you mentioned during the lecture that you have 100,000s up to millions of these events that you have to measure. Are you able to separate them from each other? I would also like to hear Sarah weigh in on this a little bit. Sarah, would you like to start?
Oh, sorry. Yeah, so I guess we're talking about some kind of stochastic background of unresolved sources. I'm not sure that we'll ever be in the situation where we could distinguish those sources. I mean, if we can localize some of them, we might be able to collect data in such a way that we can accumulate signal from one particular direction where we know But more than likely, what we'll have to measure is the background gravitational waves coming from this population of background sources. And so what we'll see is their spectra. We'll see some characteristics of the spectra that can tell us about the masses, the spread of masses, and potentially the spins and other things about the population. So in some sense, we can use that to do population statistics for these objects.
I see. So if I paraphrase you a little bit, it's going to be more difficult to specify the characteristics of individual sources, but for population purposes, where you say this many have these characteristics and this many have these characteristics, this is what it's going to be very useful for.
Yeah, that's right. For the ones that we can really distinguish, we need them to be sufficiently loud that we can see them above we can use our algorithms to pull them out of the noise.
I see. I have an immediate follow-up from the audience. In that gravitational noise background, could there be some hints of dark energy? Is it possible to invoke some dark energy knowledge from measuring this stochastic background that you mentioned?
That's a good question. So I know people are thinking about this. I myself don't know the details of how we extract dark energy physics from these signals, but I do know that we can start to measure the Hubble constant pretty well. But in this case, we're doing it more with resolved sources. So from black hole systems that we can map to galaxies that they came from, so we can measure the redshift, or binary neutron star systems where we see an electromagnetic counterpart, and then we can also measure the redshift. So those are the types of systems that allow us to measure the Hubble constant and contribute to cosmology in that way. Yeah, I don't know much details about how, maybe others know about how we start to measure dark energy.
I'm curious, is there somebody in the panel who would know whether whether we indeed can say something about dark energy by measuring the stochastic background of gravitational waves? So this whole sea of many gravitational wave sources.
I think that the real problem here is that the models of what dark energy does are not sufficient right now to say how they would influence gravitational waves. It's very hard to look for something that you don't know. I mean, as Sarah said, you can easily measure Hubble constant, hopefully very accurately, and not so far in the future. But if you don't have a model of what the dark energy does to your system and how it influences the gravitational wave, it's very hard to extract this. And I would say, yes, I'm pretty sure that there might be something in the background. And as soon as we know more, I'm pretty sure people will go back to the data. Happens often in history that, once you know what you're looking for, you go back to the data and you say, why didn't we see it already 10 years ago? So I'm looking forward to that time.
Yes, the time when we already know the answers and then look back that we could have known this before. Actually, Stefan, now we're talking to you for a moment. A question from the audience is, will or are the current detectors and maybe the future detectors also sensitive to what goes on the other side of the world? For instance, some airplane that flies over, or the moon, the planets. Can you say something about the motion of Jupiter using your gravitational wave detector?
Oh, that's an interesting one. I mean, for sure, if you look at kind of, we keep our systems very much controlled and try to isolate them very much. Okay, so there are systems which keep the mirrors where they should be, but obviously in order to keep them where we want to have them, you have to steer them and feed back signals, to compensate for effects. And one of the biggest ones on there is obviously the moon. If you look at, how do you have to align your mirrors and look at the trends over days and so on, obviously you see the moon and things like that in there. So you see certain things in there. I'm not sure. I personally haven't looked at kind of Jupiter or things like this. But for example, one thing that people find quite interesting in the gravitational wave detectors is to look for Earth modes. So kind of, obviously the Earth has some resonance modes, which again, like with the neutron stars, tell you something about the equation of state of the Earth. And that's quite interesting to look at. But Jupiter, I don't know.
Well, with respect to the question of Jupiter was mine, but the influence of planets, I think, is a very good question. But you say the moon, yes. Planets, not too certain.
Yeah, I haven't looked. I don't know.
There's a question, there are multiple questions that are very closely related, so I'm going to ask this to all the panel members. Are there less obvious things that you can expect to measure using gravitational wave physics rather than the known things like binary systems? Colliding neutron stars, colliding black holes, these sorts of things.
I can give one example, just one of, because it was kind of for 1 year part of my career, so to say. When I was a PhD student, there was a claim that that actually space-time is only 3-dimensional rather than 4-dimensional, and this kind of, you know, quantization of the dimensions causes a so-called holographic noise, which you know, some scientists claimed was limiting the noise, some unexplained noise in the GEO-600 detector. And I mean, that, I think if that would have been true, you know, we're all living in a hologram, that would have been, you know, equally spectacular, I would say, than for example, detecting gravitational wave, and that came completely out of the blue. So I think this is now off the table 10 years on, but I think things like that, you know, I'm sure there are many out there.
I'm going to take this question and stretch it out a little bit more. Maybe a question that we can ask is not so much what are the unexpected things that we might expect, but what is your favorite thing that you would like to, exotic thing that you would like to see measured using gravitational wave detectors? So Stefan Danilishin, can I ask you? Outside of quantum mechanics on a microscopic scale?
Outside of quantum mechanics is already an oxymoron. So, because everything is quantum mechanics. Well, I don't know really. So I'm really curious, as everyone, as we saw by the questions, about the dark matter. So also we don't know anything about the dark energy. So, but I do not see any ways for now how to measure it with the gravitational wave detectors. But I cannot exclude that somebody will come up with this idea. Maybe somebody from the audience.
Who knows? Or of their students. Yes, I know that there's many audience members who are teachers in education, in physics. Maybe I can pass on the question to Frank Linde. Frank, is there anything that you would really like to see measured with gravitational wave detections now or in the future?
Yes, I'm not sure whether we can measure it, but I can tell you my dreams would be to look at the very early universe. We have the cosmic microwave background, and I think that's already fantastic, even though it's not so early universe, 300,000–400,000 years old. My dream has been for a long time to measure the primordial cosmic neutrino background from a few seconds after the Big Bang. That's a lot closer than the cosmic microwave background. And I really hope that my successors will eventually measure the stochastic gravitational waves background from inflation or so. And then we really have very young pictures of our universe. And I think that's by far the most challenging we can ever achieve, I think.
Yes.
And more expert gravitational waves people can tell me whether this is possible at all. But this will be my dream for the future. And I hope to witness it before you have to put me under the ground. Okay, or whatever you want to call it.
Well, the future is very bright in that respect. We can expect many things. Sarah, to round off this round of questions, is there anything that you would like to see measured if you had the choice in the matter?
Yeah, I've got a couple. So what I'm personally interested in are really spinning massive black hole binary systems. So that's my personal interest. But I think in the future, it would be great to be able to shed light on exotic physics, whether it's neutron star matter or quark matter or dark matter with the detections that we make, or cosmic strings. I'll also add that I recently read a paper, to go back to the planet question, that LISA will be able to detect gravitational waves from exoplanets, so large exoplanets with short orbits. So that's one way we can start, helping to provide physics for an entirely different astronomy field.
It's nice to see that gravitational wave physics seems to encompass so many other sciences, right? It's cosmology, we've seen quantum mechanics, particle physics, nuclear physics, instrumentation. I'm going to Stefan to round up the Q&A session. Stefan, what would be your preferred thing?
Yeah, I think in the short run would be subsolar mass black holes that tends towards the primordial black holes, and in the longer run, I share Frank's ambition to somehow go back and see the black hole. But let me throw one interesting one in for the very young generation. How about measuring the warp drive of a spacecraft? Just saying.
As in some other civilization has made a warp drive and we measure their resulting gravitational waves?
Yeah, why not? Must be some disturbance in space-time.
Well, that is true. I want to refer people to the Star Trek movie First Contact, where they actually find, where the Vulcans find Earth in that way. Just nerding out for a moment there. I think we are at the end of our question session. There were some questions that unfortunately had to go unanswered. If you feel that you would still like to have the answer to that question, you can contact me personally at gideon.koekoek@maastrichtuniversity.nl, and we'll try to either relay a question to an expert and send you back the answer, or try to answer it myself. So if your question was not in the Q&A session right now, don't worry, you will get your answer. Having said that, I want to thank the members of the panel very much for their insights and sharing their expertise on the matter, and for being here, of course. And the same goes to the whole audience for being here on your Friday afternoon and showing your warm interest in our very exciting field. Short foreshadowing, we plan to do a similar session after the summer holidays, specifically geared towards high school students and their teachers. So please keep track of the NNV calendar, and we will promote this as the time comes along. And having said so, I will gladly give the floor back to Diederik Jekyll.
But you've already rounded it up so neatly and well, and so I would like to thank then the speaker and the great panel, and you and Noortje for all this hard work. And it's been very interesting, inspiring, and I'm sure that everybody is screaming and shouting and applauding towards their computers, which is weird, but it's the only thing we can do at the moment in these crazy Corona times. But really, I've learned so much. Thank you so much. Keep on doing this inspiring work. And I personally, this is not an NNV standpoint, but I would love to have a big Einstein telescope thing in Maastricht, Randwijk. That would be awesome. But that's just my personal opinion. Thank you so much. Have a very nice day and a wonderful weekend. Enjoy the sun. And we will see each other at a later date. Thank you.